Oh yeah, so let me repeat myself to the microphone this time so that you can hear me. I'm Ali, I work at Facebook, and I work in the Hip Hop Virtual Machine group. We're building a virtual machine for PHP that works for x86. We have a JIT for x86 that we are now porting over to ARM, retargeting to ARM. So we are interested in learning about some of the techniques that others have used for dynamic code generation and optimization for ARM.
So I'm John Masters, and I guess I run the Red Hat ARM team, and in Red Hat we obviously have a tools team doing regular toolchain work. We also have a couple of guys that are currently porting OpenJDK to V8, so we've got a bunch of different uses there.
Hi, I'm Richard Earnshaw. I'm the overall tech lead for the GNU Tools activity within ARM, with oversight of both the 64-bit and 32-bit development.
I'm Matt Grettendown, as I said. I'm toolchain working group tech lead. So we've got responsibility for the GNU toolchain for LLVM, so static compilers, both AArch32 and AArch64.
I'm Owen. I also work for Facebook on the HipHopVM team. Yeah, so Ali already sort of gave the rundown on what we're doing.
So, have you actually started looking at have you started looking at AArch64 CodeGen at all yet, or?
So Owen's been doing the work. So Owen's been doing all the engineering work on this, and we just heard from him yesterday or 2 days ago that we've got the interpreter running. We haven't started on the JIT yet. There are some practical first steps we need to do, like we need to be able to assemble instructions into memory, but we don't have the instructions encoding, so we can't get started on that yet. But we've been beginning to only think about how we would do some of the translations for ARM for some of the things that we've done for x86, but we haven't gotten started on it at all yet.
John, what's the status of OpenJDK? Let's talk about JITs first.
Okay. So status of OpenJDK, I mean, the best thing anyone can do who's watching or in here is they can look up the talk that Andrew Haley and Andrew Din gave at FOSDEM a few weeks back. They actually ran through a working example of their code. They ran a Hello World program, which in Java, I know it takes hundreds of thousands of instructions. I think it might take 1 million or something. It's pretty crazy to run Hello World. So they have an interpreter. They have a JIT in progress. It's very early days, but it's moving forward.
So when we were discussing this, it was sort of sharing code was the good idea. So sounds like some code you would like to see shared is things like how do you assemble an instruction into memory and that sort of.
Yeah, I mean, just to start with, what are the instruction encodings? It doesn't have to be code. I mean, just giving us the instruction encodings would be a start. That way we can decide whether we should do our own assembler into memory or whether we should share code. And also we want to have a disassembler, of course, so that we can dump out the code that we're generating along with the IR and the bytecodes that we have. So that would be like the first step. We have, I'll hand it over to Owen because we have some like more detailed questions around like, okay, we'll have to assemble big 64-bit constants into registers. That's something that we do all the time. It's easy to do in x86, but how exactly should we do this efficiently in ARM? We know how like the basic code sequences would look like, but we're very concerned about code size.
Yep.
And a lot of our performance problems are around iCache misses and ITLB misses, and so a lot of the optimizations are around trying to generate very tight and short code sequences. And so what we want to, some of the things we want to discuss is what are some of the good, some good code sequences for some commonly occurring idioms that would generate very short code. Things like around branches, we sometimes have to generate branches very far distances. How could we do that efficiently? What are some of the best known methods that people have experimented with? Maybe we haven't yet because ARMv8 is new, so maybe there's not many methods known yet.
So this was probably one of the things I was thinking actually would be the thing. If I imagine this session going, what would I want as an outcome to actually be? We've decided somewhere where we're going to share this, because I don't think we necessarily as you just said, know all the answers yet.
Mm-hmm.
But actually having somewhere where we can share this information, where it's possibly on a wiki, but it's public,
Right.
but we keep the editing controlled so that it's not everybody chipping in, but that we've got people who can say, actually, this is a good sequence.
Yeah,
And we can build up a step of, this is code generation. Because actually that will probably then help
a lot of people. Yeah.
lots of people, including the people designing the CPUs, if they know, oh, these are code sequences we're going to see
Yeah.
coming our way.
Yeah. So, I mean, some of the other problems, like we have to modify branches as we link things dynamically. So we'll generate code where we might branch to a trampoline, and then once that trampoline resolves itself, it'll go back and patch something. We want to make sure that we've got that correct architecturally. So there's a lot of questions like this that we'd like to discuss.
Okay, cool. So what I'm going to say is possibly we can't discuss them all because I think
Yeah.
they need a whiteboard, and this is the code I'm trying to
Right.
generate today. But I think if we can go away and say, this is the sort of thing, so things like
Right.
constant generation and whatever. So knowing what the issues are that you have, and we can share those. Do you want to talk?
So, sort of to take it back up a level, I think we have a lot to learn here in particular because our system, unlike GCC, LLVM, I don't know if OpenJDK, how many architectures OpenJDK targets, but our system has only ever targeted a single machine architecture, which is x86-64. So as it's grown and evolved, that assumption has sort of explicitly or implicitly influenced its design. And one of the things I was hoping to learn is sort of how to design a code generation system that's relatively free of these assumptions and that allows for good code generation both in a richer instruction set like x86 or RISC like ARM or ARM instruction set. And I know, GCC and LLVM have already dealt with this problem. Presumably they have some, stack of internal representations that lets them generate good code on both CISC and RISC instruction sets.
So let's take LLVM because that's sort of got the most easily get-atable IR representation to play with. That has, yes, it has its IR representation that you can feed in, do an optimization, feed out, and see how that translates. So that's something to look at, possibly, if you want to see what an IR could be. But I think actually when you look at it, certainly in the static compilers, as soon as you start compiling, you are making platform decisions. There is no such thing as a machine-independent IR. That as soon as you start compiling, you are making machine-dependent decisions. And so actually you just have to work out where do I need to put hooks so I can make different decisions in my IR, make my IR flexible to describe both situations. But things like, so not necessarily something you have to deal with in a JIT, but in a static compiler you've got a calling convention. What registers, what parameters go into memory, what parameters go onto the stack, and how's that laid out? That you start making that sort of decision as soon as you go in. You have to start using that sort of information as soon as you start translating the source code into IR from the syntax tree into IR. So that's very early decisions you make. Maybe you don't make that decision in a JIT because you're defining your own calling stuff. I don't know how. I've not done JITs myself, so I don't know how that particular area works. Yeah. So that sort of information you do have to start. So yes, the trick is to define an IR that's flexible enough to describe everything you need to describe and then work out where.
Yeah, that was I knew everything was sort of going to revolve around a good choice of IR. I mean, most of the science of code gen revolves around just how you represent in your IR. I don't know how much specifics we're going to be able to talk about today, but
Yeah.
yeah, I feel like that's the main thing we need to learn.
Renato, so as our resident LLVM expert. So what do you think about the LLVM IR as sort of a starting point or looking at something to see what it's like as an IR representation?
You mean as trying to,
Cogem from it,
for both x86-64 and ARM64?
yeah, and also speed of being able to use it and things.
So one thing we learn quite early when dealing with LLVM is that IR is not target agnostic. So you will have in the front end decisions that will target different backends. There's no way you can generate, unless you're being very naive or your usage is very simple, you will have some differentiation in the front end. Maybe you can get away with many things, for instance, like pointer sizes or address size, things that you can assume, oh, it's only 64-bit. But then it's so small that to save time and space with these things is actually silly. So you better be very explicit in your IR and try to comment up later the things. So I've seen many problems appearing because somebody was trying to be smart in the front end and actually making things much harder in the middle and the back end. So if you can be extremely explicit in your front end and generate an IR that is verbose, it's ugly, it's weird, but at least is exactly what it means. And then in the middle end, you simplify things. In the back end, you ignore things. That has worked well in LLVM.
Actually, yes, there's a recent example from what we're looking at in GCC where we're trying to remove redundant sign-in zero extends, widening and narrowing, and actually one level of IR, the RTL, is not the right place to do it because you've lost signed information. So, and you have to move up to the tree, and that adds all sorts of other things. So generic IR, keeping as much information as you can around for as long as you can. You can always ignore it if you don't need it, but that's quite useful. Richard, do you have any comments on any of this at the moment?
I think you've covered most of the main issues at this stage. I mean, obviously there are decisions that we have to make in the compiler because we're conforming to an ABI, which is an external specification. In a JIT, you do have the flexibility to define your own procedure call standards because you only have to be self-consistent, not externally consistent. Unless, of course, you're making calls to a runtime interface. But presumably you will distinguish those compared with your internal calls. Your internal APIs for calling between code, you can pick whichever conventions you think are appropriate. And they may even change from call to call. You have that flexibility, which you probably don't get in normal compiled code, statically compiled code. Examples would include things like variable promotion, so sign extension of smaller types. Do you do it in the caller or in the callee? If you do it in the caller, then the callee has to trust it, which means that you've got slightly more risk of security holes. If you do it in the callee, you lose some opportunities to eliminate redundant code.
And actually, the other thing is this a client or a server JIT? Because they've got different. So if you've got a client JIT like in JavaScript, you want to get the code going as quickly as possible. You don't care about the
So basically, we're building a server JIT, and we can. We're worried about compile time, but I think we're not as worried about compile time as we'd be on a client, and certainly not as worried about the size, the memory footprint of the JIT as we would be on a client. But we do still want to have good startup time. And we are looking at very aggressive strategies like profile-guided optimizations, just like the Hotspot VM does. Now, we have a kind of a very unique environment. It's nothing like Java or C because PHP has its own unique challenges with dynamic typing. And like we have the linkage we have between caller and callee is complicated because of all the different cases we can have for various things. So yeah, I think some of the things that I'm worried about is that I'd like to learn from folks is really just at the code generation strategies of what are some good code sequences for ARM v8 for various things. And it sounds like this is something that hasn't been fully explored yet because ARM-v8 is still very new. Some of the things might look similar to previous generations of ARM, but other things are new. So that's really what I'd really like to learn about. And maybe one thing we could talk about is how do we set up something so that we can all share practices. And also I'd like to know what's the state of like LLVM for V8? Do you have code generated?
So we have the basic GCC. At present, we've been focusing primarily on feature coverage. We need to have enough of the various the basic compiler you can write in a few days. Writing a full port of GCC takes months to years. We've been working on the GNU compiler since the architecture was in its early days of specification, and there are still features that we're adding today, whether it be new instructions like the Neon extensions and the vectorization capability, or whether it just be features that are going into GCC now for essentially security hardening and related activities. Some of these are primarily needed for debugging, some of them are needed for particular environments and options. But until we have the full set, we can't claim to have a complete compiler. Where am I trying to go?
So I have a question for you guys. So one of the things that, so we like to do everything in the open source. So the compiler that you see, the HipHopVM that you see on GitHub is only at most a week older from what the latest trunk looks like for us internally, right? And we do everything in the open source. We like to keep things in the open source. So one of the challenges that we're going to be faced later on is there'll be more than one implementation of the ARM-v8 architecture, right? There'll be different microarchitectures, different instruction widths, different issue widths, different pipeline latencies, and so on. And we'd like to be able to allow microarchitecture-specific optimizations. So things like scheduling for a particular implementation, as an example, right? And we wouldn't want to see like versions of hip-hop that are not open source but optimized for a particular architecture, a particular implementation of the architecture. So one thing we're thinking about is how can we build a system where you can have, say, a configuration file, an ops file, some people call it, where you can say, here's the latencies, here's the pipeline constraints, here's the issue rules, and so on, and then feed that to a generic scheduler, and then have different hardware vendors provide that. That's kind of the thought that we have currently, but I was wondering how LLVM is going to deal with this issue.
Not very nicely. The problem with LLVM is that all the hardware information is generated from the table gen files, and that's statically compiled it's generated at compile time, which means the whole backend needs that information, and that doesn't change from call to call. And it will be very hard to make it change from call to call, but also the one thing I'm asking, trying to propose in the list is, instead of saying, is this Cortex A8? Is this Neon? Is this blah? Is saying, does this have a feature A? Rather than, because they know that Cortex A8 has some things and A9 has other things. So if you ask, is this A9, then I can do whatever out of order thing would work. But the better question is this out of order? Does this have any penalty between VFP and Neon? Name the features rather than name the things that have the features.
Do you have those?
No.
Okay.
It's all named by stuff.
So do you model latency? Do you model the latencies between instructions and pipeline hazards and memory latencies and things like that?
There are descriptions of the pipeline issues.
So GCC does have a very complex model for describing pipelines. It's a full finite state machine system that you can describe a particular CPU. There are then a number of cost tables. And I think the best way to do code gen when you've got multiple targets is don't even describe features. Certainly don't describe CPUs or test on a CPU. don't even describe just features. What you need is the cost of each sequence. And then you pick based on the most efficient sequence on the CPU, based on the costs that you've got for those instructions that it uses.
That is still a selection decision. But that is still an instruction selection decision. If you're looking at scheduling, there are different ways in the literature about how you can go about writing a hazard recognizer. And GCC pretty much implements one such hazard recognizer and
So
has specification languages for it.
So for example, what's the best strategy for ARM? Is it bottom-up or top-down scheduling, for example? And what are the heuristics that work well?
I think it's quite hard to answer that. We've only ever done the GCC version.
Okay, and
Which is a standard list scheduling algorithm.
okay, top-down list scheduling.
I think, yes, it starts at the head of a block and works
Okay.
down. There was a previous implementation that started at the end of the block and worked up. Each one has its merits and its disadvantages.
Of course, one of the problems of getting costs is getting it out of your hardware vendor.
Right.
And
There's two trivial models right now.
see,
We put in 2 examples, mainly just because we wanted the framework right for the compiler. The numbers we put in were made up.
Okay.
Well, they were copied off of an existing core.
So how important was all that for existing hardware, like ARM v7? Let's use an example since there's hardware out there. Does this all make a difference for the various different implementations of it?
Yes, it can make a big difference.
How much of a
Certainly,
difference?
certainly 5 to 10%.
Okay.
The more out of an order the core is, the less scheduling becomes relevant. But if it's an in-order core, scheduling is vital.
there are other optimizations. So the classic one is the fact that A15 has been, if you look at codegen for GCC for A15 compared to the other cores, it stops using LDMs as much, the load multiples. It goes to the load doubles, load pairs in AArch64 speak. And that makes a big difference. So there are other things apart from scheduling that, as you say, just general instruction selection.
It's worth saying that the fundamental. I should probably speak in there. Sorry. Yeah, it's worth saying that some of the fundamental. There's a lot of overhaul has happened, right? Not just in the instruction sequence being changed and things being deprecated that are in the v7 architecture, but also A15 is the first time you have that sort of really out of order kind of approach being used. So I think it's just starting to become more. I don't mean to interrupt you, Richard, but
No, sorry. Perhaps one of the most important things is how good the core is at doing branch prediction, because that has significant impact on code generation strategies. If your core has a very good branch predictor, then the only time that you would probably want to avoid branches is when the sequence, the pattern that's driving that is unpredictable, because it's data dependent in some way and that data has a random pattern. In those cases, you want to use conditional select type operations wherever possible.
So one of the things, so you were asking about assembling and disassembling and getting access to the encodings and all that, and I'm not going to go into like encoding documents, but a lot of that information is already there, right? You can download the binutil source if you want to get encoding sequences today. You could do that.
Doesn't tell you what instruction does that.
Yeah, it's true. It doesn't tell you everything, but we do have disassemblers, for example, already. So if you want to just get, so what is it you guys? Maybe you could explain what it is that you actually need in the way of those tools. So maybe we can go through what tools are available today and answer that question
Well,
as well.
I think there's 2 things. One is just basic things we need in order to get a functional system up and running, and then these kinds of issues of, what's the best code selection strategy,
I don't think the instruction encoding is a big deal.
No, I mean, we'll get that somehow, right? It's mechanical, right? So that's not the biggest issue. That's just
So what tooling was it that you actually felt you were missing right now?
Well, I think the reason we wanted to come here is really learn more about some of the best known methods to generate code, because ARM is relatively new to us. We're very good with x86. We've been doing that for a couple of years and tuning that. And so we wanted to learn more about just shared experiences, like some of the stuff that you guys just mentioned about what kind of loads to select, is very valuable for us because we saw that there's a sort of a scatter-gather type of instructions that we know that we could probably use, and if that's a good idea, then okay, we'll take that away from us and with us and use it.
So, in the perfect world, Richard's on the hook, but I think it's probably easier if Linaror take it.
So I think the only thing I can draw on is that somebody within ARM wrote a Cortex-A programmer's guide. Something's going to be needed to cover V8 as well.
Right.
It's writing a good, readable document of this nature is quite hard, and it needs a lot of work to get it right.
Yeah, like the example, like Intel has that manual that says here's how to generate good code, right? Use these code sequences, don't use those code sequences. So if something like that would be...
Those are very good for assembler people writing things by hand.
Or compiler writers.
Compilers, well, compilers in the end are deterministic, and use this, don't use that is only the first step.
Sure. But like we don't have that step right now for ARM.
Another issue here is that it makes more sense for Intel to write something like this because Intel controls the microarchitecture. Whereas with ARM v8, there's going to be plenty of different microarchitectures from different hardware vendors, and they're all going to have different, at least slightly different characteristics and with regard to how you want to write code for them.
So if you look at the Linux community, it's sort of, currently it's ARM v7a with the integer stuff, and VFP v3d16 is the hard float, because that's sort of the architecture that most people, or is the baseline architecture that most people seem to have implemented. Others will have Neon on, but and so that code's got to work. I think there is value in us saying, okay, for ARM v8, AArch64, here's the code sequences we think for various operations. What are the best code sequences for this? Because actually then if we do that and we put it in public, it's somewhere that anyone can read, including people producing chips.
So without going into any specific details, because I don't think this information is public yet, the things you would probably want to assume is that loads are going to take 2 or 3 cycles to return data. Most cores are going to be 2 to 3 way issue, and if you're in order, that means try to fit as many instructions as you can between a load and its use. Try to avoid too many sequences where you're using the result of the previous instruction in the next one. Put other instructions in. Try and essentially interleave operations as much as you can. That's going to be true regardless of what the code is. And then once you get beyond the basics, some instructions are clearly going to take longer than others. Floating point instructions typically will take more cycles than integer instructions. Most integer sequences will probably take 1-2 cycles at most. The more complex the instruction, the more likely it is to take more cycles. You can probably write some heuristics without knowing the details and generate some code which is likely to run fairly well, if not very well, on almost any V8 core without knowing the specific details, if you take those sort of guidelines into consideration.
But for out-of-order cores, that's less of a concern, right?
Out-of-order cores will benefit, and what they will be able to do is pick other instructions when a particular stall comes in and execute those. So they will just get, they'll get rid of some of the corner cases that it's hard for software writers to deal with.
But I think
So one of the primary ways that we've been tuning x86, and this goes to a tooling question, is by looking at the hardware performance counters and using perf, for example, and looking at executed branches, branch mispredicts, looking at the sample data to see which instructions are causing branch mispredictions or icache misses or decache misses and things like that. What's the state of the performance counters on different ARM processors? Is it standardized or?
there are some standard ones, and there are some extra. There's obviously spaces where you can add extra ones. And
Are they comparable to what x86 has?
I must admit, I don't know. I've not done a comparison between the two. I know there are cache misses, and you can say how many instructions have been architecturally executed and things. Obviously, the foundation model doesn't have a complete set because it's a.
So there's a few things here. First of all, foundation model, if it has a PMU, I assume it does. I wouldn't rely on those numbers for anything. If it even counts, the value it does count. Well, it has something which is like monotonically increasing, but it doesn't really mean anything. It may be the number of instructions, it may not be. Particularly when you go to idle, it may just add a number onto that. So don't use them. Yeah, that's what I'm saying.
Yeah,
So
we're kind of waiting for
don't
the
use
hardware to do that.
In terms of hardware, the architecture has, it doesn't mandate even a PMU, I don't believe. If you do have one, then there's an event space which the architecture does define, and it says this event number in hex must correspond to this string of text, and you can go and look what that string of text kind of means, and there's some scope for variability there because people do lots of funny microarchitectures and you can't just nail that down. It doesn't mean that they are mandated to be implemented, it just means that you can't use that hex number for something else. Cycles is a pretty standard one, so that's the easy one to get, but like you say, the more interesting ones, mispredicts, that kind of stuff, you need to go and look at the TRM for that.
Okay.
And they naturally become very microarchitecture specific. We don't have some of the features that x86 has, so we don't have a lot of the Encore stuff. We don't have a lot of the, I can't remember what it's called, PEBs or something, and the branch stack profiling as well. We don't do any of that. But there should be enough for you to get a good idea, at least at L1, of things like TLBs, things like cache misses, and your IPC, that kind of stuff, which is probably what you're after for this.
Just going back a step, I would.
Does the class model have instruction tracing capability?
Yeah.
So there is something called Tarmac Trace, but I don't know it's available. I don't know if it's available to. It certainly won't be in the foundation model. It requires you. It's quite cumbersome to use. You have to throw another library at it, and you have to state upfront the cycle at which you'd like it to start. You can't turn it on and off.
Yeah, I mean, I don't think we'll get to much performance tuning with the foundation model. I think we'll just get to functionality and just going to wait for hardware to do anything performance-wise. It's slow enough to. I don't think we'll even get. It's going to be difficult to write a JIT using any kind of simulator because you're simulating the JIT itself too, and that adds a lot of execution time. So I'm not sure we'll be able to get much use out of the foundation model for selecting the code.
Come earlier,
Yeah, I think so.
you get there.
That's right. Yeah, that's true.
But actually, generally, I think tuning for a generic ARM v8, especially if you're going, well, actually, you might do things like PGO because, yeah, the 53 and PGO profile guided optimizer. Because certainly, I think the Cortex A53 and the Cortex A57 have been announced in a big little configuration. So if you've got big little on your core, you might actually work out which different bits of code are going to run on different CPU type microarchitectures. So when you do. So, excuse me, Cortex A53, Cortex A57 are like A7 and A15, they're a big little pairing. So you can get a SoC with both chips and you end up running code on different ones depending on what your kernel how your kernel decides to schedule them. And so actually that's
probably not an issue in the Facebook servers.
Probably not, no. Big cores all the time, yes. Big. Cool. But generally, an ARM v8, an AArch64 generic tune to start with, and then knowing what you've got and tuning that down.
Yeah, I think first order, what we want is to understand just basic code selection, and like we have to jump really far away. What's the best way to do it? You know, how should we lay out the branches to jump around, or you know, there's cold code here, hot code there. How should we deal with that? And we're going to call really far away. How should we do that very efficiently? You know, we have these sequences with a lot of branches. They're unpredictable. You know, how should we use the select instructions? I know the select instructions that you have on ARM are richer than what's on x86. We do use select, the cmove instruction on x86 for a couple of our code sequences, and we're hoping maybe we can get better use out of select on ARM, because there are some few code sequences that are very unpredictable, because PHP is a dynamically typed language, so there's a lot of switch on type of code sequences, and the types sometimes are predictable, sometimes they're not.
So one of the possibly unique instructions in the ARM and AArch64 instruction set are the conditional compare operations, which mean that you can often fold away a lot of logic that forms complex decision graphs into conditional comparisons. They take some getting your head around, but once you've done that and you've generated the infrastructure to generate those instructions, they can in some programs have a massive benefit, because they fold away a lot of quite difficult conditions.
Yeah, we have one code sequence that's very challenging, which is our reference counting code sequence. So PHP is reference count, it's not garbage collected. And the reference counting has to be done precisely. So whenever the last pointer to an object goes away, right then you have to run the destructor for the object. And the code sequence that we have for incrementing and decrementing a reference count is has like 3 branches in the general case, because we have to check for the type to see if it's a reference counted type or not. And even if it is, there's some special cases for those that are. And then at the end, we have to check whether we should, in the decref case, execute the destructor or not. Right? So that ends up with being a code sequence that has at least three branches in most cases.
You do have conditional increment and decrement operations in AArch64.
Okay.
So they should be useful
Right.
for these
But you know,
purposes.
like sometimes executing throughout the whole code sequence and then doing a memory operation might not be the best thing, because now you're executing redundant memory operations.
You don't have conditional loads and stores.
In which case, then we can't use it, because the reference count is in memory. So we'd have to do a speculative load. I mean, we know that it won't fault, so we can do the load.
You
But
could do the load, and then you could do
like
conditional add.
right,
then-
then do the store back.
Yeah.
But then, and it's not clear that's a win, because now you're always doing a load and store for all cases, and it might be better to say, you know, that's cold, we'll just move it out of line and we'll jump to it if it is reference counted. It's not clear, right?
I think that's the only thing you're going to find out that by profiling it and
Right.
seeing what the performance impact is.
Right.
If you're hitting the same location very often, then it's going to be in cache and it's probably not a problem, unless, of course, you're trying to share this code between multiple threads on
Well,
different CPUs.
it depends. And it depends on, like, you know, the load store unit, whether it has the bandwidth to support all those extra loads and stores, because there's plenty of other loads and stores that happen in the code, right? So adding more might not be a wise strategy, right? And it also depends on how good the branch predictor is. If the branch predictor is able to predict those accurately, then having a branch might be better, right? So it comes down to the microarchitecture, I think.
And I think you're probably also in a fairly unique position in that you've got the exact code you want to run on it available as you're developing your JIT, because you've got the whatever the
Yeah.
PHP that Facebook runs, you can use that as your benchmark.
Yep, that is what we do. Yeah, that's exactly what we do.
Whereas, well, OpenJDK and GCC and LLVM get, garbage in, garbage out type stuff, or really nice code. And we've got to get it right for everything. You've got a...
So for GCC and LLVM, what's the experience for compiling large server applications? What are some strategies that are beneficial for ARM? Or is that sort of still very new and we don't know yet?
I must admit, we've not really tried it yet. Most of what we've compiled is not much more than Spec 2K or Spec 2K6. Even those, until we've got real hardware, we can't really evaluate them in great detail.
And it's a case of, we need the workloads so that we can benchmark them and improve the compiler. GCC is an LLVM to an extent, is a blended compiler. It's got to target it's got to target embedded, mobile, server enterprise, networking, all those different targets. And whilst in theory anything that makes Cocoa faster is going to be of benefit to everyone, there may be cases where a trade-off has to be made.
bit of a tooling question. So people have sort of mentioned disassemblers a bit earlier. So if you're doing a JIT, it's kind of nice to be able to disassemble what your JIT has just output. There's a disassembler in binutils, but it's GPL3, so you can't necessarily just link it into your JIT. So I was just wondering, is anybody thinking about doing a permissively licensed disassembler chunk of code? Because it seems like the kind of thing that might be useful to share around.
Anyone? Anyone?
I guess that's a no then.
Well, we might end up doing one. Yeah, exactly. If we write one, it'll be on GitHub in our source space, and everyone can use it. I think we use a Zen license.
Okay, cool. So I make it, we've got about 10 more minutes before the next session. So what are the next steps? So
You writing a guide.
me writing a guide, okay. No, I think it's been dumped on me. I think the way to do that would be to put something on the wiki and just put, and have it sort of, here are the questions, here's what we think the answers are currently.
Rather than waiting for an official guide, we want to develop it in the open.
I think that's a reasonable outcome. Richard, Romano?
Yeah, and I think take a look at some existing code gen sequences. Nobody's saying that what GCC generates today is perfect. There's a lot of work to do yet on tuning, but if you go and look at some of the handwritten assembly that's already creeping into the Linaror Cortex strings, there's some examples there of how the architecture might work that may be of interest to people to go look at.
So yes, Cortex strings, for those who don't know, is Linaror's got a repository of hand-tuned routines, and there's stuff there for AArch64 in a generic way for string copy and mem copy, I think, and string compare, and things like that. And it will grow over time. It's not very big at the moment, but it will grow over time. So final comments, let's go round. John, anything else you want to say, ask?
As long as you write the guide.
Okay.
So are any of the hardware vendors tuning GCC for their hardware, or what's their experience? Do we have any representation here?
There may well be, but they haven't told us yet.
Yes, and if they have, they can't say. Owen, do you have anything further to add?
No, I think so.
Cool. Anything? Cool. Richard? Oh, so any questions from the floor?
The tools perspective, DS5 versus Perf, do you prefer DS5? The Perf tool? Perf.
I don't know how DS5, what DS5 does. Wait, do you know what DS5 does?
Performance control.
I'm sorry, I don't know how DS5 works.
Hey, I'm Venkat from AMD. We do tuning for the GCC specifically for AMD processors, and specifically we work on spec 2006, and we have a kind of come up with some quick reference guide for developers, particularly in what are tuning features we need to enable to generate better code for the particular versions of the processors. So maybe we can do similar to that.
Cool. Anything else from the floor?
Actually, I think that's sort of feedback for the hardware vendors, which is, please actually publish these kinds of tuning guides, right? And a compiler writer's guide would be very valuable for all the different microarchitectures. I can't hear you. Maybe you can speak on the mic.
Yeah, it's there in our website. We do publish
For
that.
ARM?
Yeah.
For ARM?
No, this is for x86.
Oh, sure, yeah. So we're familiar with that, yeah. I think we need it for ARM now, too.
Yeah.
So I think my action is to try and get that started through the Linaror. Cool. Anything else from the floor? Cool. Okay. Thank you all very much.